All right, getting on into lesson 4 of chapter 24.3. So moving on into the next section, we are now writing equations of lines. So we're taking all the information that we've come up with so far and finding gradients and x coordinates and y coordinates, and we're now using those to write the equation of a tangent line. So the first one's already been done for us, so let me just kind of talk you through this example. But let me give you the overall idea first. Anytime you're going to write the equation of a line, we need a point, which means an x and a y coordinate, and a slope. That way we can use this point slope process in order to do that. And so point slope formula looks like this. So y minus y1 equals your slope times x minus x1. So you can see the three things that we need in this is a y coordinate, a slope, and an x coordinate. So they're going to somehow or another give you some of that information, but we're going to have to use our derivative knowledge to come up with whatever's missing here. But we need those three things for any problem. So we have this function right here, and to start for this problem, all we were given was the x coordinate of -2. So we knew this value, we knew this was -2, but now I have to use that to get the slope and the y coordinate. So first things first, one thing we've talked about in some of the earlier lessons, where do you get a y coordinate? Right? Remember, that always comes from the original function. So if we take -2 and sub it into the original function, that's what you're seeing in this line right here. That gives you the y coordinate. So we got the 1 that's going to go right in here for the y coordinate. And if you take -2 and plug it into the derivative, and that's what you're seeing over here on this step, that gives you the slope of -3. And now we have all the pieces of our puzzle. So we have the slope right here, -3. We got the y coordinate of 1. We have the x coordinate that was -2. And all that goes into the point slope formula. It looks just like this. And now if you get y by itself, you got the equation of your tangent line. So if we were to take a look at the graph, the 2x squared plus 5x plus 3. So if we put that into our calculator and graph it, so there's the original function. If we graph that, so this tangent line, -3x minus 5, if we graph that one as well, -3x minus 5, so you can see that's just the tangent line. A tangent line hits our graph in one spot right there. It just passes through. So what we just found was the equation of that tangent line at the value where x equals -2. And if you look right here on the graph at -2, right, that's where those two graphs intersect, is at that point right there. So that's what we just came up with that equation. So moving on, equation of the tangent line to the curve. That's parallel to this one. Now, with all these problems, keep something in mind here. This all comes back to this one formula. So no matter what they give you to start with, you always need three things. You need a y coordinate, a slope, and an x coordinate. So you always need those three things. In this problem, if our tangent line is parallel to this line, well, what does that tell you? We know parallel lines have the same slope. So since the slope of this line is -3, that means our slope is -3. So they basically just told us that the gradient is -3, which means I still need an x coordinate and a y coordinate. That's what we have to start with. So if our gradient is -3, consider what we've done with that in a previous lesson. That means that the derivative is -3. So let's work with that idea. So here's the original function. If we find its derivative, right, we're going to do the 2x minus 2. So using the power rule, we can get the derivative is 2x minus 2. So that's the derivative that we have to work with. We know that the slope equals -3, which means that the derivative equals -3. And we can now use that to solve for x. So if we add the 2 over and then divide by 2, it looks like we get -1/2 for x. So we are almost there. We now just need a y coordinate. And remember, where do you always get a y coordinate from? That always comes from the original function. So now if I take my -1/2 and plug it into the original function for x, that's going to give me the y coordinate to go with him. So if you sub that in for x into the original, it looks like you're going to come out with 9/4. as your y-coordinate. But now there's all the information that you need, and we just go to the point slope process to get the equation of the tangent line. So now if I do y minus the y-coordinate of 9/4 equals my slope times x minus the x-coordinate. So that's the setup right there. You got to do a little cleanup though. It got double negative, so let's change that to a positive. Distribute the -3, add 9/4 over to the other side so that you can get it into the slope-intercept form. If you do all that, and a lot of that could be done in a calculator, you should get y equals -3x plus 3/4 as your answer. So that's where that one would finish. But typically we are looking for slope-intercept form on that. So if you're an IB student and you're taking the IB test, you can actually leave it in point slope form if the directions don't specifically tell you which form to leave it in. They do accept the point slope answer, so keep that in mind. Example 3, we got 2 more to go, so find the equations. So we got a couple here of tangents to the curve. There's our curve at the points where the gradient is 0. So remember, the other way they could word that is by saying something about horizontal tangent lines, because horizontal tangent lines also have a gradient of 0. So anyway, if we go through with our process here, if we find the derivative using our power rule, we should be looking at 3x squared minus 12. Constant goes away. So there's our derivative. So in this case, again, just like the one up above, we know the gradient is 0, which means the derivative is 0. And now if we solve for x on that, you would add the 12, divide by 3, square root both sides, and you got plus or minus 2. For x, don't forget the plus or minus. If you leave that out, you're going to miss half the answer and miss half the points. So don't forget the plus or minus in those cases. But anyway, again, we're looking for equations of tangent lines. So something to keep in mind, if you have a 0 slope, what kind of a line is that? That's a horizontal line. Well, how do you write the equation of a horizontal line? Right, it's always y equals something, so just consider this for a minute. Right, if you were to have a tangent line, let's just say, I'm just making one up right now. Let's just say you wanted the equation of this line right here. It's a horizontal line, so whatever the y-coordinate is the equation of the line. We would just say y equals 2 is the equation of this line, right? Now that's not our answer. I'm just throwing that out as an example to remind you what the equation of a horizontal line looks like. So similarly, our answer needs to be y equals some number is the equation of a horizontal line. So let me get rid of that so you're not confused. That's not part of our answer. I was trying to give you that example. But if these are my x-coordinates, well, then what are the y-coordinates? So if I plug those into the original function, as always, if I plug in a positive 2, then I get negative 14 for him. And if I plug in negative 2, I get 18. So if we're going to have the equation of a horizontal line, I just look at the y-coordinates, just like I pointed out right here, to write those equations. So in this case, I'm just going to have the equation y equals negative 14. And in this one, it's going to be y equals 18. And so those would be my two equations where they have 0 slopes. All right, going on to the last problem here. Equations of the tangents, equations of the lines tangent to this parabola. So first off is where it is horizontal. So where would it be horizontal? Remember, we know what that now means. Every single time, that means your slope is 0, right? And it's just going to be y equals some number for that line. So we know the slope is 0. On this, if you were to expand, so if you were to do the x plus 2 squared, so let me just write that out, plus 4x plus 4, bring down the plus 1 there, and add in the plus 1, I now have x squared plus 4x plus 5. So that's just the same function, just put into friendlier terms for the way that we use it. If I find its derivative. We know we're going to need that, so let me just throw it out there. So 2x plus 4. So remember, if it's a horizontal line, it's just like in the last problem. It's just going to be y equals some number. Well, in this case, what is the y coordinate? If I take the derivative and set it equal to 0, because my slope is 0, that means my derivative is 0, 2x plus 4. And if I solve that equation, I subtract the 4 and divide by 2. Then negative 2 is my x coordinate. And if I plug that into the original function, you get the y coordinate. In this case, if you plug that in, you get a y coordinate of 1. And since it's a horizontal line, that's all you need. You know, one way you probably could have come up with that answer even without the algebra involved or the calculus involved. If you think about this for a minute, something you've seen in the past is this is what they call turning point form. So we already know the vertex is at -2, +1, and you can graph that in a calculator to test that if you need to. But we know it looks like this. And if you think about what we've talked about in the past, I know in this area the slopes are negative. I know in this area the slopes are positive. Well, what happens from negative to positive? You get a 0 slope. That always occurs at a max or a min, just like I've shown in some of the previous lessons. So if I know that my horizontal tangent line or 0 slope occurs at a max or a min, that means in a parabola that would occur at the vertex. And so that's why it's no coincidence that these results are the same. So we could have come up with, if you just understand this concept, I really could have come up with that answer right just by looking at this without even having to do the calculus. But anyway, the calculus works too. So last one. In this case, it is simply perpendicular to this line. So first things first, let's get y by itself. So if I subtract the x over and divide everything by 3, we can see that the slope of this line is -1/3, which means the slope that is perpendicular to that would be the opposite reciprocal slope, which is +3. So we know our slope is 3. We simply need the x and y coordinates to go with that slope to write the equation of the line. So we know the slope just like we did up above in example 2. We need to set the derivative equal to 3 in order to get the x coordinate. Once you know the x coordinate, you plug that into the original function to get the y coordinate. So if we take the derivative that we already found out right here, 2x plus 4, and set that equal to 3, then x becomes -1/2. So we now know the x coordinate is -1/2. If I plug this into the original function, I can get the y coordinate, which, let me just tell you, comes out to be 13/4. And now I can do the whole point slope process to get the equation of the line. So y minus 13/4 equals my slope times x minus -1/2. So there's the point slope version. But of course, we want to get y by itself because you do want to get in the habit of putting those into slope-intercept form. So if you do properly solve for y, here's what it's going to come out to. So you can give this a shot. Make sure you're doing this correctly. But that's where it would finish off. And again, all I did on that was distribute the 3 and then add this over to the right in order to get y by itself. And that's it.